First of all, I want to thank you for inviting me to this series of seminar. It's a pleasure for me. And as you said, I will just make a very easy review on some results on the entanglement entropy. And I have to tell that a very similar version of this talk is already online that I made on GGI tea break some years ago, but I removed a lot of material and I introduced a lot of new material. So to give a complementary view on the entanglement entropy, even always making a review. But let's start easy. First of all, you all know that we are currently living a second quantum revolution. In this second quantum revolution, we have some devices that are called NISQ, which is an acronym invented by John Preskill that stands for Noisy Intermediate Scale Quantum Era, in which we have some quantum computer, but they are not yet enough performing, in the sense they are noisy, okay, they don't keep coherence well enough, and they are not large enough to have all quantum supremacy. And this is one of the reasons why there is a huge boost in quantum technology, but in quantum science in general. But this talk will not be about quantum technology, not about quantum computing, but will be more on entanglement, which is a deep property of quantum mechanics. And what is this entanglement? We all learn in basic course in quantum mechanics that a state like this one, which is a singlet state of 2 qubits, is entangled. In the sense that if I measure one, I know the outcome of the other, even if a priori I will not know the outcome of the measure of one spin. But what we can do with it? What is this entanglement? And I must say that historically it really depends to whom you ask and mainly to when you make this question. Because for many years, at the birth of quantum mechanics, it was merely considered a spooky action at distance, as Einstein said, and it had no particular quantum advantage, let's say, to use modern word. But in the 80s and 90s of the previous century, it was made clear that is the essential resource for all quantum technology, quantum computation, quantum communication, and quantum information. All the speed up that we know in quantum algorithms are due to entanglement. But this was something related to the quantum information itself. It really became a tool even in statistical physics and condensed matter at the beginning of the new millennium, when it became a tool to study and characterize new states of matter. And in fact, only in the last 10 years or so, it became very popular also in the high energy community as a fundamental tool to understand the laws of nature. And in fact, this is one of the main reasons why I'm happy to be here, because I will give an overview mainly from the point of view of statistical physics and condensed matter, but all I will say it has profound consequences also for high energy physics, and some of them I will mention. So, as you know, in 2022, the Nobel Prize of Physics was awarded to Alan Specht, John Clauser, and Tendon Zellinger exactly for revealing entanglement between photons. And this was a great achievement that was done more than 40 years ago, and that led to Nobel Prize to these 3 pioneering experiments. But not only, last year Nobel Prize also went somehow to something similar, which is the discovery of macroscopic quantum mechanical tunneling in electric circuits. So in a macroscopic object, you can reveal quantum mechanical effect. And this is exactly one of the lines where I want to go, moving the interest of entanglement from few body entanglement to many body entanglement. In fact, few body entanglement is something that has been studied theoretically and experimentally since many decades now, and it's at the basis of many famous and inspiring results in the literature. But instead, many body entanglement is something that became a mature field only in the last 20 years for what concerns theory, but even less than 10 years for what concerns experiment. The first experiment on many body entanglement really dates back to 2015-16, so 10 years ago. And this will be the real topic of my seminar, which is the many-body entanglement. And by the way, despite being very modern field, it already got some attention even on the Starmer press. For example, I report here an Italian comics in which, in this comics, the main character, Martin Mister, discuss about ER equal EPR conjecture by Maldacena and Saskin to realize some wormhole to travel from very distant places. And this to say that this concept of many-body entanglement, even if very much abstract, already have been popularized and became subject of science fiction and popular magazine and literature. And in fact, the goal of this talk, we are slowly arriving to the right point, will be to show maybe too many apparently unrelated results in disparate fields of physics that have a common denominator, many-body entanglement. And the main goal is, as written here, is to convey the message that many-body entanglement brought new and fresh ideas for a deeper understanding of nature. For example, as I said, it got very much popularized in Science magazine. These graphics that I found online, and it's updated only to 2015, shows how the number of preprints with the word entanglement, the title in the FTH archive, and you can see that while up to the year 2000, it was basically a non-existent word, it had a boost in the last 20 years, and this boost continued nowadays, which is still keeping increasing, as I just observed by searching on the archive, but I don't have the proper graph done. And these third plots show one of the other ingredients of this talk that will be the experimental verification of all these nice ideas on many-body entanglement. Okay, but without further ado, let's move to the real protagonist of this talk, which is the entanglement entropy. How it is defined, this entanglement entropy? We start from a pure quantum state psi, whose density metric is just a projector on the state itself. Then we divided the Hilbert space corresponding to this state in two parts, HA and HB. And usually a pure state is not a product state. So we can construct the reduced density matrix of A as the trace over the degrees of freedom belonging to the B Hilbert space of the full density matrix. And the entanglement entropy is nothing but the von Neumann entropy of this reduced density matrix. And this is a measure of the bipartite entanglement between A and B. One thing that is very important is that for its definition of the entanglement entropy, we only need to specify a bipartition of the Hilbert space, but in the remainder of the talk, and for what concerns most of the literature that you can find, this bipartition corresponds to a spatial bipartition of the system. So you really divide the space in which the system lives in two parts, you induce a bipartition in the Hilbert space, and then you proceed with this partial space to get the entanglement entropy. But now we have defined this quantity, how we can compute it. As I said, the general state, you can imagine a state of qubits or spins, will be a very large superposition of base state with many coefficients, which usually are 2 to the n coefficients if n are the total number of spin. It's clear that if you want to just encode this state in a classical computer, it's extremely difficult because as n becomes larger, this 2n coefficient becomes really a barrier to encode this state in the computer. In fact, even in the few cases that you know exactly the state, for example, from Bethe ansatz or other exact knowledge that you can have, calculating the entanglement entropy, it's a real nightmare numerically, because you need to extract the reduced density matrix from this huge matrix of coefficients. So you will need a quantum computer to do that, but we don't have yet a quantum computer. The second possibility is always the one that it's available to theoretical physicists, is to develop an appropriate theoretical or numerical framework. And This theoretical framework is exactly what we start building in 20 years ago now with myself and John Cardy, which is the replica approach to the entanglement entropy. Our first observation is that the Feynman entropy of the reduced density matrix can be written as the limit for n that goes to 1 of the derivative with respect to n of trace of rho a to the n. This is a basic observation, which is really elementary, and it's at the basics of all replica approach to compute logarithms of operators, also in disorder system. But what is important in the present case is that trace of rho a to the n for any integer it's a very natural and simple structure. In fact, can be obtained by sewing cyclically cut plane, and the result, as a result, trace of rho a to the n is nothing but a partition function of what is known as an n-sheeted Riemann surface, at least in in space-time dimension, which is equal to 2. If the space-time is larger than 2, obviously this is not a Riemann surface, but it's a surface that has some similarity with the Riemann surface in 2D. And what is very important, that always in 2D, you can write this partition function in a Riemann surface as the 2-point function of some very special twist field, which live in the replicated theory of the original, of your original theory that usually in the literature is called the mother theory. And so these are, those are particularly operator, which in the conformal field theory in particular will be primary operator. And this trick to compute the entanglement entropy is at the basis of all our results, especially in 1 plus 1 dimension, but also in higher dimension. Some basic results, for example, are now part of the prehistory of the entanglement entropy. For example, that is, if psi is the ground state of a local gap Hamiltonian, which in field theory language
Pasquale, can I ask a question?
Yes.
Yeah, sorry, on the previous slide, I just wanted to ask in practice, if we can't compute, so this limit is defined by analytic continuation from all the integer renues. In practice, if I can only compute a couple using some numerical methods, how quickly will my resulting approximation for the entanglement entropy converge? Or do I have
There are very nice techniques to find, obviously this is a numerical method. There are nice numerical techniques to extrapolate and to make this, to make the interpolation in a numerical manner. So you extrapolate to the interpolation. And this, for example, there is a nice paper by Eric Tony and collaborators on that. But you need something like 10 moments in order to get a decent result. With very few Q3, you cannot extrapolate to n equal to 1.
I see. Thank you so
much. You really need a lower bound to get a decent result would be around 10 moments.
Thank you.
But this is a very appropriate question. And yes, please, I didn't say interrupt me at any moment. I'm happy to answer on the spot. And make it even more likely, because I really don't see any of you, so I don't have any clue if you are following me or not. So, as I was saying, one of the main results is the area law, which states that for local gap Hamiltonian or massive quantum field theory, the entanglement entropy is proportional to the area that separates A and B. The first one proposing this area law probably was Schrödinger back in '93, and from then there are many evidence that the area law is correct, and in fact has been rigorously proven by Astic in 1D, and it's conjecture in general dimension. But probably the more famous result in the field of entanglement entropy is the main violation of the area law, which was pointed out by Olsen, Larsen, and Wilczek back in 1994, which states that for a 1 plus 1 dimensional conformal field theory, the entanglement entropy of an interval of length L embedded in an infinite system is proportional to the logarithm of the length of the subsystem with a coefficient in front that is 1/3 of the central charge of the conformal field theory. This is a violation of the area law because, as you see, the area in 1 dimension will be just the number of boundary points, which in this plot will be 2, and instead, so should not scale with L. Instead, the entanglement entropy grows with L like log L, so it's a violation of the area law. And what is more important is that the prefactor is proportional to the central charge, so in some sense it counts the number of degrees of freedom that there are in the theory. And nowadays, the entanglement entropy became the most effective way to determine the central charge in numerical experiment, and even in real experiment, by the way. Okay, this being said, what we can do with these results? One first application is of the area law is the observation that the area law states actually are a very tiny fraction of the states that compose the entire Hilbert space. If you pick at random an Hilbert space, it will have extremely high entanglement entropy, which will be proportional to the volume of the subsystem, not to the area. So the area law states are really a small minority of the total state. So if we know that the ground states of local Hamiltonian belongs to this tiny fraction, if we are smart enough to imagine numerically algorithm that will make us search for the ground state only in the part of the Hilbert space that satisfy the area law, we will have an exponential gain in the for the search of this ground state. And in fact, one of the meaning of the entanglement entropy is the exponent of the entanglement entropy is the minimal amount of classical information required to specify the state psi. So it's clear that to specify a ground state, we don't need 2 to the n for a system of n spin, but we need much less. And that's the goal, to find algorithms that are able to search in this reduced Hilbert space. And there are many algorithms that do this nowadays. They are known as tensor network state. And this is together a powerful set of numerical methods based on the entanglement content of a quantum state. The most popular one is the matrix product state, which are the implementation of what is known as the density matrix formalization group. And these are very well designed for one-dimensional system. Another object that is extremely powerful for one-dimensional system, especially for critical one, are the MERA. And if you want to go to higher dimension, you have to be more ingenious and get more refined algorithms, like, for example, these PEPs that state for projecting entanglement pair states. And that Subil said, nowadays we have an alphabet soup of proposal with whom you can really try to simulate your quantum system with a classical computer. And this was possible only thanks to our profound understanding we had of the entanglement content of many-body quantum system. But as you have seen, we introduced the replica trick just as a trick to numerically access the entanglement entropy, the fundamental entropy, but with the time, actually, this revealed a very powerful tool also in experiment. In fact, what was first realized in 2015 in the group of Marcus Greiner in Harvard was the realization of a two-copy of a system, exactly like we did in our field theory, but this time in a cold atom experiment. And by properly coupling and designing what is known as swap operator in this artificial quantum system, they were able to measure the entanglement entropy of a real cold gas. And the results are shown in this experiment and in these plots here, and are very nice. For example, in this first plot here, you can see the transition for what is known as a Mott insulator, which is a gapped phase of matter, so satisfy the area law, to a superfluid, which is basically a free boson in field theory language. And so free massless boson, and so it is a conformal field theory, and there's a logarithm violation of the area law. And you can see from this plot, you pass from an entanglement entropy, which is saturated, so it's constant, to an entanglement entropy which grows with subsystem size, and so shows the typical logarithmic behavior of a conformal field theory. And this was mainly better analyzed in this plot here, for example, where you see the This is a finite system, so the logarithm is actually smoothed to a symmetric curve, but because of the finite temperature, this curve is not exactly symmetric, but it's a bit asymmetric. But all in all, what we have is an entanglement entropy that really resembles the result of the conformal field theory. So making it on the lab, in spite of having a very small system, in this case was a 6 particle system, still you can see many signatures of what are known to be the one of the underlying field theory. And in fact, I want to show also another development I want just to mention here of the entanglement entropy is the famous holographic entanglement entropy. In fact, in the framework of ADS-CFT correspondence, Ryu Takai and Haji, exactly 20 years ago, proposed the formula that nowadays is extremely famous, that the entanglement entropy of a region B here is equal to the area of the minimal surface of in the RDS space, which is anchored to the surface B of the subsystem size. Obviously, this surface is not the flat surface because the geometry here is not Euclidean, but is anti de Sitter, and so the minimal surface goes deeply into the bulk and at some different value from the volume of B. And this formula now is extremely famous, and it is at the basis of the idea of Van Ramstok and Nadar that you can actually build the entire space-time with quantum entanglement. But this was only a parenthesis in the realm of high energy physics, because I want to go back in my comfort zone, which is statistical physics, and I want to discuss now what is the relation between entanglement and symmetry. Let's assume, for example, that psi is a state that is symmetric under the reaction of a given charge Q, which means that the projector on the state, which is the density matrix, commute with the charge. And this charge obviously is local in the sense that it can be divided in the charge of A plus the charge of B. If we take at this point the trace over B of this commutator, we get the elementary formula that also the reduced density matrix commute with the charge restricted to A. This implies not that rho A has a definite value of the charge, but that rho A has a block diagonal form, each block corresponding to one of the possible value of the charge within the subsystem A. So we have these blocks in this way. In formula, you can write rho A as the decomposition of rho A into the symmetry charge by Q, and you can normalize each of these blocks to rho A Q. So you can normalize to 1 in such a way that so you divide by the sum of the eigenvalues or by the trace of this matrix. In this way, rho A Q becomes a putative density matrix well defined with trace 1, and this you can use to define the symmetries of the entanglement entropy, which is just the entanglement entropy of each symmetry sector. And this is an extremely interesting field that started just in the last less than 10 years. The first very important paper on the subject was one of Moshe Goldstein and Eran Sela, which showed how to make this calculation in conformal field theory of the symmetries of the entanglement. And exactly because of this, it would deserve an entire talk only the symmetry resolution of entanglement, but I introduced this mainly to explain what happens when the symmetry is broken, which will be the goal of the next 20 minutes or so. So now we have a state that doesn't commute with the charge, which means that the reduced density matrix is not anymore block diagonal, but it has some off-diagonal elements. From this full matrix, one can define a symmetrized density matrix in which one projects out all these off-diagonal elements simply by taking the sandwich of the reduced density matrix between two projectors of a given symmetry sector. So each element in this sum is one of this matrix, and when we make the direct sum, we obtain all the blocks of the reduced density matrix. So this matrix is by construction symmetric. The entanglement asymmetry, which measures how much the symmetry is broken in these states of reference, is just defined as the difference of the von Neumann entropy of the symmetrized density matrix with respect to the von Neumann entropy of the original density matrix. By definition, that I will not show exactly why here, this quantity is positive and is equal to 0 if and only if the two matrices are equal, which means the initial state is symmetric. You can understand then why this is a genuine measure of how much the asymmetry is broken, because only when the state is symmetric you get 0, and as soon as you break the symmetry, this quantity starts growing and becomes larger and larger the more the symmetry is broken. And exactly like for the entanglement entropy, even for the asymmetry, one can do the replica trick and introduce the Rényi version of the asymmetry, which are just constructed with the moment of the reduced density matrix, exactly like before. Again, we introduce this as an analytical trick, but we will see that it's very important in numerics and in experiments. This quantity found its main application in the quantum Bembe effect, and on this subject there was a very nice thermal seminar by Sara Murciano, so I will not repeat what she said here. I will just say that to drive your curiosity, that the quantum Bembe effect is the fact that a system that initially is break more the symmetry, actually it can restore the symmetry much faster than a system that initially broke the symmetry less. And this not only has been measured, theoretically predicted, but has been measured in this very nice experiment that is reviewed in the talk of Sarah. But now I want to move about what entanglement entropy and asymmetry can tell us about black hole. In particular, about the black hole evaporation. You all know, actually you know much better than me, that black hole evaporates through radiation emission, as was first pointed out by Hawking 50 years ago. But the semi-classical calculation of Hawking leads to the very controversial result that the radiation entropy increases linearly in time, and this brings to the famous information paradox. One of the easiest solution of the information paradox is due to Don Page, and the main idea of Page is that the black hole and the radiation can be approximated by a random state of qubits. And this idea goes back to 30 years ago now. So you have a random state of qubits in which part of it is radiation and part is the black hole. Let's see in a cartoon what was exactly the idea of Page. At the beginning, at time t equal to 0, all the particles are inside a black hole, and so all these random qubits belongs to the black hole. And the radiation is the empty set. As time passes, some particles go out from the black hole and become radiation, and so you have that random qubits that initially were thought as part of the black hole now should be thought as part of the radiation. As time passes, more and more particles get out of the black hole, and finally, at the end of the evaporation process, there are no particles left over in the black hole, but all particles are just in the radiation. So, if we believe in this very naive argument by Page, and we say that these particles are always in a random state, it's just their location that moves from inside the black hole to outside the black hole, we have to make a very simple calculation in random state, which is an elementary calculation of random matrix, to find the result that as long as the number of qubits that are inside the black hole is smaller than L over Q, the total number of qubits, the entanglement entropy grows linearly with a prefactor that is equal to log Q, and after that it decreases linearly and goes to 0. In fact, the entanglement entropy of a pure state should be symmetric about its middle, and this is so. But now, this is a calculation of random state. The idea of Page is that we can interpret the subsystem size that appear here as the time of the black hole evaporation. And if we do so, we get the famous Page curve for the entanglement, or for the entropy of the black hole, that initially it increased linearly, exactly like predicted by Hawking, but halfway to the evaporation, the entanglement entropy starts decreasing and it slowly go to zero, in such a way solving the information paradox, because at the end of the evaporation process, you are still in a pure state in which all the particles are inside the radiation now and not inside the black hole, but the entropy of this state is exactly zero, as it should be by quantum mechanical law. And this is extremely nice idea. And actually, the card that I showed you before here, it's for an infinite system. One can make a calculation for finite system, for example, and showing that the page curve is approached very quickly as the subsystem size increase. For example, here you see the result for the second Rényi entropy of, and this is the exact result, analytical result for the second Rényi entropy for arbitrary subsystem size. And you see that as the subsystem size increase, you very quickly approach the page curve that already at L equal 20, which is a very small number for what we are used for, it deviates from the page curve only in a small set close to the half of the system.
Pasquale,
now, yes.
Pasquale, could I ask a quick question? Sorry, for non-specialists in the black hole theory. So at the time when Hawking was writing his paper, he was thinking not about entanglement entropy, but the classical entropy, if you will.
Yes,
and so in a
right.
sense, right, and so that is proportional to, the Bekenstein-Hawking entropy is proportional to the area of the black hole. So even at time t equals 0, that entropy is non-zero. So I'm just want to be cautious equating the sort of the thermal entropy that Hawking and Bekenstein had in mind and the entanglement entropy of the radiation that somehow, talks about mutual information between what's outside and what's inside the black hole. Could you maybe comment on that?
Yeah, okay. My understanding of that is that this entropy we are discussing here of the radiation is actually an extensive process, as clear from this formula here. Okay, so it grows linearly and indeed it's scaled like the volume of the subsystem, or the volume at the middle of the evaporation, like the volume of the system in total. Mm-hmm. So it's an extensive thing. The initial entropy of the black hole is satisfied the area law. So I would expect to be in this construction a subleading effect with respect to what we are interested here in describing the entropy of the radiation. Anyhow, if you want really to be precise, probably the best thing to do is to consider the mutual information. Yes.
Okay, thank you.
As you said, I think that's, you will remove this small quantity that anyhow will be subleading compared to this one. And my understanding is that people talk indistinctly about entropy and mutual information exactly because it's a small effect. It's area compared volume, so it's small. And that's why people are ignoring it.
Okay, awesome.
But to be precise, you should do as you said. And now, my next question is, what about symmetries of in this black hole evaporation? And this was a paper that we published just a couple of years ago together with Filiberto Ares, Sara Musciano, and Lorenzo Piroli, and in which what we did is to compute the entanglement asymmetry of a random state, and then interpret this in the sense, in the logic of the black hole. What we obtained by this calculation of entanglement asymmetry, which again is a quite easy calculation with Wingardner calculus, is that the entanglement asymmetry in thermodynamic limit is exactly zero if the subsystem is smaller than half of the system, and it becomes, it jumps sharply at half of the subsystem to a value which is proportional to the logarithm of the subsystem size. And in finite size, this sharp curve that here is the red one is smoothed, obviously, as shown here. What we learn about this result for the black hole? We learn that any symmetry, because which symmetry I'm discussing here is really immaterial, because this is a random state, so it can be any symmetry. actually is always restored by the radiation before half of the radiation is really emitted. So before halfway of the black hole evaporation, you cannot know if the black hole initially was symmetric or not, only by looking at the radiation, because the radiation will be completely symmetric in any case. And you need to see what happened after the radiation has been emitted in order to understand that the initial black hole actually was not symmetric, as a normal black hole would be. But there are also symmetric black holes, as you know better than me. And actually, this very nice result can be interpreted in terms of the decoupling inequality by Adrian and Pasquale, which tell us that the reduced density matrix of a subsystem is extremely close to the identity in the sense that it's bounded by Q, the LA minus LB, and you see that if LA is smaller than LB, so the radiation is smaller than the black hole, this object is exponentially small. In the opposite case, it's exponentially large, and this bound doesn't tell us anything. But so it tells us that before half subsystem, the radiation actually is in a state that is extremely close to the identity, and the identity is clearly symmetric with respect to any symmetry. And that's how we can interpret this result a posteriori. Always take care that the expectation value of functional of operator is not equal to the functional of the expectation value. So this was not completely guaranteed, but we found the result that is compatible with this intuition. But symmetry, not only symmetry, physics is an experimental science. And as soon as we got this very nice result, we thought, is it possible to measure nice effects in an experiment? And so we went in contact with some experimentalists in China, in Hangzhou, that they have some extremely performing superconducting qubits with whom they can produce random states. I will not enter here in the way to produce a random state of qubits by a series of Floquet circuits. It's something very standard in quantum circuits. What is more important is that we could measure entanglement entropy and asymmetry by a technique that is known as randomized measurement. A technique that is so important that I want to discuss even afterwards, so if time permits. So I will not tell any details on randomized measurement right now, but I will want to show the results of this experiment done in China. So what we did was to prepare a set of random qubits with this protocol, and we prepared qubits of states of dimension 5, 7, 9, and 11. And the results of the entanglement entropy, the second reigning entropy actually, which is the only one that can be measured in experiment with this randomized measurement setup, are shown in these plots here as symbols. And these are compared after error mitigation with the results obtained from Page. So this is the Page curve that I showed you before. And you see that the agreement of the entanglement entropy with the Page curve is really fantastic. There is it's even smaller than the error bar. And the same is true for the asymmetry. Here we see the results of the asymmetry after error mitigation always for finite size, which are exactly those plots that I was showing here before theoretically, shown against the numerical result, the experimental results with these superconducting qubits, and the agreement is exceptional for all value of subsystem size, showing that so this is one of the first experimental evidence of the Page curve in a real experiment, and also the asymmetry Page curve that we can see here. But not only we can probe symmetry and entanglement, we can even probe higher quantity to measure entanglement, in particular the negativity. and one can reconstruct what is known as entanglement phase diagram for those states. This will be something quite complicated, but let me just say that now what these people invented in these two papers here is that if you instead dividing the system in two parts, you take a tripartition, and you study the negativity between A and B in this tripartition. Negativity is a good measure of entanglement for mixed state that I was planning to say in this talk, but I don't think I will discuss because time is really running fast. So if you study negativity, you get three different phases in this negativity. One that is positive partial transpose, which means that there is no entanglement at all. Two region of maximally entangled, in which the negativity grows linear with subsystem size, and a region of saturation of entanglement in which the negativity is constant. What we are able to show here that this phase diagram actually can be reproduced even with our small system in the superconducting qubits. And here you see the results of the experiment. These dots represent the points that are actually measured, and the curves that you see here inside are just interpolation of the experimental measured dots. And you clearly see, in spite of the smallness of the system, this phase where the entanglement is basically almost zero, with a phase where the entanglement is large and saturated in the center, and with instead a maximally entangled phase that is developing on the right and on the left. More than these 3D plots, maybe it's not so much clear. What is more instructive is a cut. These two plots here represent two cuts of this density plot, one along this line here, and one in the vertical line here in the middle. So one that goes between the maximally entangled phase, the entanglement saturation, and maximally entangled. In thermodynamically, this will be a linear increase followed by saturation, followed by a linear decrease. In finite system, these curves are smoothed, theoretically as predicted by this line, and the experimental data fall exactly on top of the theoretical line at that subsystem size. And the same happened for the cuts here at LA over LAB equal to 1/2, which is the cut, I repeat, on this line here. So we see that with this superconducting qubit, we can not only probe entanglement and symmetry, but even higher quantity like the negativity. And this is extremely nice. Concerning random state of qubits and the page curve, I cannot not mention that the idea of page is based on this assumption that a random state of qubits approximate a black hole. But how realistic is this? Is there any theory of gravity, even approximate theory of gravity, that actually is in agreement with this idea? And this was exactly what done about 5-6 years ago in these two groups separately by Maldacena et al. And by Stanford et al. Basically, in what they proved in these two papers is that in model of JT gravity, as is shown here, actually you can reproduce the page curve for the entanglement entropy, and the fact that before this curve was not found, but was only found the linear increase of the entanglement entropy was due to the presence of new saddle points in the gravitational path integral as written here, and this saddle arises in the replica method that simplifies wormholes connecting different copies of the black hole. And that's why these ideas are called replica wormholes. So we have some macroscopical quantum theory of gravity, obviously not the quantum theory of gravity that we don't have yet, but some theory of gravity that reproduce the page curve, and this is extremely important, and this is a pictorial representation of what is known as a replica wormhole, a saddle that connect different replicas. So to say that this idea of page that I'm advertising here is not so peregrine, but it has some foundation even in the quantum theory of gravity. So this will finish the story on the random states, on quantum random state. If you have question on this setting, I would like ask you to make now, because I will move else to something else.
Pasquale, this is
Yes.
Andrzej Niewiadomski. I'll ask a very, very quick question.
Yes.
So you found, to summarize the part about the asymmetry, you start with a symmetric black hole. You look at the evaporation in your numerics, and you find that the sign of the asymmetry becomes apparent after the page time. Is that fair?
Yes, that's exactly what we find.
And so what is the physical interpretation of that? That somehow the black hole remains symmetric up to a page time, and afterwards...
No, the radiation remains symmetric.
Oh, sorry, the radiation remains
The radiation
symmetric.
remains symmetric up to the page time, yes.
Right.
Exactly
And then afterwards, in what sense is the symmetry broken? Does it mean what? The black hole...
the radiation shows it's not symmetric any longer. Because the initial black hole was not... the information that the black hole initially was not symmetric is passed to radiation only after the page time.
I see. Okay, so got you. Understood. Thank you.
And that's really it's really the point of this result. So thank you for asking. Other question on this? If not, let's move to entanglement in non-equilibrium quantum system. That maybe will be the last, or maybe not. I will have time to discuss something else. So I want to discuss now non-equilibrium quantum system. The idea is to prepare a many-body quantum system in a pure state psi naught, which is not an eigenstate of the Hamiltonian, and then let it evolve with unitary dynamics. In this case, the reduced density matrix is defined as usual, and I will tell that a stationary state exists if the limit of the reduced density matrix for any finite subsystem exists, and we call it ρ infinity. What is the thermalization of this non-equilibrium quantum system? I will say that this object thermalizes if we consider the Gibbs ensemble for the entire system, so e to the minus beta h divided by z, and then we take the reduced density matrix of this thermal ensemble. If the reduced density matrix of thermal ensemble that we can call ρ is equal to ρ infinity, we will tell that the system thermalizes. Notice that in this equality there is a lot of physics. In fact, ρ infinity is the reduced density matrix of a pure system. So a state that in total has exactly zero entropy, and the entropy of ρ infinity is the entanglement entropy. While ρ is the reduced density matrix of an ensemble, which has extensive entropy, and its entropy is a thermodynamic entropy and is not entanglement, because it's not a pure state, and the entanglement entropy is a measure of entanglement only for pure state. So we see that we are equating two very different beasts, and this equivalence, which seems very innocuous, has very deep knowledge. In fact, we say that these two density matrices are equal. It implies that yes.
Pasquale? Yeah, I didn't understand something on the previous slide. What do you mean by large time here? Because don't you expect Poincare recurrence eventually? So this infinity must be much smaller than something.
As I said here, I'm assuming that the system is infinite, so there are no recurrence. But obviously, if a system is finite, it means before the recurrence time, as you correctly said.
Okay. So okay, I see. For a finite system, as long as it's much smaller than recurrence. Okay, thank you. I understand.
But thank you for the question. So what we obtain is that the entropy, thermodynamic entropy of the subsystem is equal by this equality to the entanglement entropy at infinite time. But thermodynamic entropy is extensive, so apart from small innocent boundary term, it's exactly equal to the thermodynamic entropy of the entire system. So we get this chain of equalities which tell us that the thermodynamic entropy is equal to the entanglement entropy. And this is very bizarre things, because what we are saying here is that for large time, the entanglement entropy becomes the thermodynamic entropy. Or, looking the other way around, that the entropy of a stationary state is just the entanglement that has been accumulating during time, which is a very different idea about the entropy compared to what we usually discuss in our undergraduate courses, and gives a new fresh light on the meaning of entanglement and entropy in quantum system. And in fact, this very nice idea was probed in this very famous experiment, always in the group of Marcus Greinet at Harvard in 2016, which the title explained all the concept without that I tell anything else, quantum thermalization through entanglement in isolated many-body system, which the goal of this experiment is exactly to show what I said before, that the thermalization comes because of the entanglement, and this quantum correlation with entanglement that leads to non-zero temperature. And non-zero temperature means non-zero entropy. And I would say that this is a paradigm shift about the origin of the entropy, and it's also from the pragmatic point of view, it's also tell us that the understanding of the quantum dynamic cannot proceed from the characterization of the entanglement. That's why nowadays, when people study this non-equilibrium behavior, the first quantity they look at is the entanglement. They don't look to local operator, they don't look to other quantity. Everyone looks as first thing entanglement because it's the quantity that tell us more on what is going on, actually. And okay, so this is the typical curve that were measured in this experiment, show that the entanglement initially grows and then saturates, which is actually the typical behavior that has been seen also in other experiment. This is another experiment with randomized measurement where you see again, this experiment is of 2019, where again you see linear growth of entanglement followed by saturation. How we can explain this linear growth entanglement followed by saturation? This behavior has a twofold explanation. One for integrable system, which is called the quasi-particle picture and was proposed first by myself and John Cardiff back in 2005, and then refined for all integrable system by myself and Vincenzo Alba. And it's based on the existence of stable quasi-particles that propagate through the system, spreading the entanglement throughout all the system. And with very simple kinematic calculation, you can see that this picture of the entanglement is spreading from initially localized quasi-particle brings to a linear increase followed by saturation. For chaotic system instead, there is another idea which is known as the membrane picture, which was pointed out by Adam Naum et al. Just in the last decade or even less. And it's a completely different mechanism, which is related to the minimal cut that you need to explain, let's say, to divide a random circuit, for example, which is a model of chaotic behavior. But this is very bizarre that the entanglement entropy followed by saturation followed by two very different mechanisms. And in fact, differences can be observed if we look at more complicated geometries, like, for example, the entanglement of separate regions, which in the case of integrable model have a ballistic regime in the sense that they scale with subsystem size exactly like shown by this triangle, but instead if the model is chaotic, the interference between quasi-particles just destroy them, and you don't have, after some distance between the two subsystems, you don't have any more entanglement between the two because this has been destroyed by the chaotic dynamics. But anyhow, this fact that the entanglement entropy is always linear increase followed by saturation really calls for a unifying picture, and this was what we did back like 4 years ago together with Bruno Bertini et al. And we proposed the idea of space-time duality that gives a unifying picture both for quasi-particle and chaotic system. But I will not delve into the detail of this. In the last 5 minutes that I have, how much I have? 5-10 minutes, no?
Yes, no problem. Yeah.
I would like to spend a few words about something that I've been using a lot, but I have not been I told the main character because this is an idea that goes back mainly to Peter Zoller and John Preskill, which is the randomized measurement toolbox. Which, if you want to know more information, there is this extremely nice and complete review on Nature Review Physics, written by the main character, Andreas Elben, Steven Flamian, Insuan Wang, Richard Kweng, John Preskill, Benoit Vermeersch, and Peter Zoller, which are the main character in this field. And what is this randomized measurement? The idea is relatively easy. We have a quantum state, like, for example, our random state that we prepared, or the ground state of some physical system. However, you have a quantum state of which you want to measure the entanglement entropy. The idea is to perform on this quantum state a set of random local unitaries. Okay, where by random local unitary, I mean, I literally means the product of local operation on each of the qubits, which is random, completely random. So this is a local random unitary, and then we perform measurement after these random unitaries. Now, if we make this operation many times, so we construct a set of random unitaries, we measure one time, we measure a second time, we measure a third time, and let's say we measure k time, and then we change unitaries, and we repeat the operation, we measure k time. We change again unitaries, and we measure again k time. In the end, we will end up with the k measurement for each of the n independent unitaries, which in total will be k times n bit strings of length n, where by bit string I really means 0 or 1 for each object, okay? So that's the procedure, I repeat. We make long random unitaries, and then we measure in a basis which is called the computational basis, which is completely arbitrary, but we fix it. Once we do, we always measure in the same basis. And we measure in this computational basis, and every time for each qubit we get either 0 or 1. And we collect the results of this experiment. Now, from this set of randomized measurement, randomized because you made these random unitaries here, you can construct many, many quantities. In fact, the motto of the randomized measurement field is measure first, ask question later. Because really, from this set of qubits, you can construct several different measurements. For example, what it has been done in the literature in the last 5-6 years with this randomized measurement. The most important for me is the measurement of entanglement-related quantities, which I will show some example in the following. But for example, what people have been able to do is even to measure the overlap, which means the scalar product between two quantum states in two different laboratories. So by collecting this randomized measurement in one laboratory, actually this one was done in one laboratory in Maryland and one laboratory in Innsbruck, they were able to construct the overlap between these two states and seeing how close they were, these two states, preparing two very different labs. What it has been possible, for example, was to probe chaos through the out-of-time order correlation. It was possible to characterize topological order, and it was possible to reconstruct, together with machine learning, the entanglement Hamiltonians of the system. So it was really possible to do things that 10 years ago would be considered science fiction. That's why I really want to spend a few words about this randomized measurement. Let's see one formula, for example, how you can reconstruct the second Rayleigh entropy. The second Rayleigh entropy, it has this very simple formula that actually was already produced by Henke and Benacker 15 years ago, which tell us, apart from some normalization factor, is the sum of the exponential of the Hamming distance between the bit string. The Hamming distance, you know, is 0 if the two characters are equal, and is 1 if the two characters are the same. So it's just a very simple object, and this is an exact formula. So the second Rayleigh entropy is simply measured by randomized measurement by this simple formula, and this is what has been measured in this experiment here or here. in this very famous experiment of 2019. But one cannot measure only the entanglement entropy. One can have the classical shadow of the entire reduced density matrix, and the classical shadow of this simple formula here. Here, UI in this formula are the randomized measurement that are the random unitaries that I was discussing before. SI are the outcome of the bit stream of the measurement, and if the average of this operator gives, it converge actually for in the limit of very large randomized measurement to the reduced density matrix itself. In this sense, this is a classical shadow because it's constructing only by classical object of your quantum state. A question that you can worry at this time is that still here I need to make an exponential number of operation, but this exponential number is only in the subsystem size, and by the way, it's much more reduced compared to the one you will do in with full tomography, and not in the system size. So in principle, with this method, you could consider a system of 100 qubits like the one that exists in our experiment and be limited to go to subsystem of the order of 10, 20, maybe 30 maximum spins, because then it will be too much to process even with these techniques. And for example, one experiment that we did with this randomized measurement was to reveal the entanglement barrier for the operator entanglement. The entanglement barrier is a very nice concept. As we have seen in the thermalization of a quantum system, you have at the beginning, the initial state is in a product state, so it should be very easy to process quantum mechanically. At large time, it's a thermal state, so also it is the reduced density matrix should be very easy to describe with the classical methods. But in the middle, there is a barrier, which it's called the entanglement barrier. In fact, this which is revealed by the operator entanglement, which is the entanglement which is in the reduced density matrix as an operator. And this entanglement, what it does, it first grows and then it decreases, showing up that at very short time, there is no much entanglement. At very long time, there is no entanglement in the reduced density matrix because we are in a thermal state. But in the middle, you have a large entanglement that actually is extensive. This was known theoretically since like 5-6 years, but was revealed by reanalysis of this experimental data. As we said, measure first, ask question later. And okay, I was thinking that I could have some time for mixed state entanglement, but this is really far too much, so I will skip this. And I will just conclude my talk by saying that I discussed many aspects of entanglement, but many fundamental results have not been mentioned during this talk. For example, I never mentioned disorder system and localization. I never mentioned entanglement in Hamiltonian and algebraic quantum field theory. I didn't mention gauge theories, topological entanglement, operator entanglement I briefly mentioned. I didn't mention many of the quantum field theory results like C theorem or quantum null energy condition. I didn't mention quantum chaos, SYK, and quantum circuits, measurement-induced entanglement transition. I also didn't mention here. So there is really a huge field that is still exploding and that I didn't have time to review here. And the take-home message that I want really to leave you is that whenever you look at entanglement deep enough, you get much more than by any other means. And with this, I will conclude here. Thank you for your time.